Yes, you're right. Right. So if n is a negative number, right? Let's say -2. Right. So if you're looking at y of -2, okay, then it is equal to x of 2. Okay. So the output at time -2 depends on a future input at time 2. All right. So thank you. So it is not causal. All right. So how about this second example here? So here y of t is equal to x of t times cosine t plus 1. Okay? All right. So show your hands if you think this is causal. Okay. All right. So show your hands if you think it's not causal. It's non-causal. Okay. So, all right. So why do you think it's non-causal? Yeah. So this is a tricky question, right? Because this is actually a causal system, right? Because the output at time t depends only on the input at time t. Okay, so this is a trick question because obviously you see here a function that depends on t plus 1. Okay, but this is not the input. Right? This is just some scale that you multiply on the signal x of t. Okay, so the output at time t still depends only on the input at time t, but it is multiplied by a signal, by a weight that depends on t. Okay? So this cosine t plus 1 is just any function of t. Right? So if you view this as, let's say, g of t, right, you probably would not think it's non-causal. Okay? Right. So thank you for the answer. So I think most people raise their hands for non-causal, so this is actually quite tricky. Right? Okay, so this is causal, and in fact, it is memoryless. Okay. Okay. So we covered memoryless, invertibility, causality. Okay. So the next property is stability. Okay. So what does it mean for a system to be stable? Okay. So intuitively, all right, we say that a system is stable, okay, if a small input, all right, may lead to a very large, possibly diverging output. Okay. So this is an intuitive example. So if you have this pendulum, right, hanging down, then and you impose a very small force to this pendulum. And suppose that the input, right, this force is the input x of t, and the output is this angle y of t. Right. So because of gravity, right, even though, because of this gravity, right, when you impose a small force on this pendulum, it will still tend to come back down to its original position, right? So you would only have a small or at least controlled output in response to a small input. Okay. But if you have an upside down pendulum like this, right? If you just impose a very small, perturbation, right? Very small input to the pendulum, this pendulum will drop down drastically. So this system is unstable, but this system is stable. Right. So other examples are such as, chain reactions of chemical experiments, the population growth with no limitations on the living space or food supply, or the bank account balance if you never do any withdrawal. Right? These are all examples of unstable systems, right? Because these systems will eventually diverge. Okay. Now, examples of stable systems are such as the RC circuit we showed before, where if the voltage across the capacitor is too large, it will discharge through the resistor, right? So in this system, it is stabilized by a discharge through the resistor R, okay? And then in example 1.9, right, when we look at the velocity of a vehicle under friction, we also see that it's stable due to this friction force that is pulling it back, okay? Okay? So these are just some intuitive examples of what we would think of as a stable system and what we would think of as an unstable system. Okay? Now, more formally, right, mathematically, we're going to define a system that is stable, okay? We're going to define a system to be stable if a bounded input yields a bounded output, okay? And this is what we call, bounded input, bounded output stable, or Beeble stable for short.